You know, when we try to build really ambitious things, I'm talking deep space probes, fusion reactors, you name it, we almost always run up against a wall, and that wall is materials. We're pushing technology to its absolute limit, and to do that, we need stuff that can survive just impossible conditions. Today, we're going to dive into one of those exact challenges, the quest for a true super steel. And we're not just talking about any old challenge. We're asking, how in the world do you make a metal that can literally live inside the core of a next-gen nuclear reactor? This isn't just a simple engineering problem, you guys. This is a material science puzzle of the highest order. So, just how tough is this environment? Well, we're talking about something called a lead-cooled fast reactor, or LFR for short. It's a super promising technology for the future of clean energy, but man, its insides are incredibly hostile. Okay, so any material you put in there has to fight a war on 3 different fronts. First, you've got blistering heat. We're talking up to 800 degrees Celsius. That's hot enough to make a lot of metals just turn to mush. Second, there's a constant storm of high-energy neutrons just slamming into it, literally knocking atoms out of place. And third, as if that wasn't enough, the whole thing is swimming in corrosive liquid metal. It's a total triple threat.
And here's the bottom line. The stuff we use in today's reactors, the trusty alloys we've relied on for decades, they wouldn't last a second in an LFR. They would fail, and they would fail catastrophically. So we need something totally new, something engineered from the atom up just to survive this.
So let's bring in the hero of our story, a special kind of steel that scientists think might just be the answer. And believe me, this is not the steel in your car or in a skyscraper. This is a high-performance alloy with a very particular set of skills. It's called Ferritic/Martensitic steel. We'll just call it FM steel. What makes it special is its high chromium content and this really unique internal structure. That combo makes it incredibly tough, and, this is the important part, super resistant to that radiation damage we talked about. So yeah, it's a fantastic place to start. But it's not perfect. It's got an Achilles heel. While it can totally handle the radiation, that third threat, the corrosive liquid metal, really does a number on it. At those super high temperatures, the steel's protective layer just gives up, and the metal itself starts to dissolve. So, our hero has a flaw. So how do you fix a flaw like that? Well, like any great recipe, right? The answer is to add just the right secret ingredient. In this case, it's a single element that can completely change how the steel behaves. And that ingredient is silicon. Yep, just Si on the periodic table. As the researchers put it, adding a little bit of silicon helps the steel form this dense, stable, protective film on its surface. It's basically like giving the steel its own personal corrosion-proof force field. The huge question, though, is how much silicon is just right. To figure that out, the scientists basically became master chefs. They forged 4 different batches of this steel. They kept all the main ingredients, like the chromium, right around 9%, pretty much the same. The only thing they tweaked, as you can see here, was the amount of silicon. They started with none at all, and then carefully added more and more, all the way up to almost 1%. And this is super cool. It's not just about mixing ingredients. Each sample went through this really precise baking process. It was heated way up to 1,000 degrees, then instantly cooled in water, and then tempered at 600 degrees. This whole heat treatment thing isn't just cooking. It's how they lock in a very specific, incredibly strong internal crystal structure. All right, so our 4 different recipes are ready. It's time to see what they're made of. The researchers put them through a whole bunch of tough mechanical tests to see how strong they were and, just as important, how tough they were. First up was a good old-fashioned pull test. Just measuring its tensile strength. And the results here were totally clear. The more silicon they added, the stronger the steel got. The sample with almost a full % of silicon was the undisputed champion of strength. So far, so good, right? But strength isn't the whole story. Toughness, which is the ability to take a sudden hit without shattering, is arguably even more important inside a reactor. And this is where the story gets a really interesting twist. The toughness didn't just keep getting better. It actually peaked with a 0.68% silicon sample, and then, totally unexpectedly, it dropped off a little bit with the strongest sample. And that right there is the big mystery. The strongest steel wasn't the toughest. So, what gives? Something must have changed deep inside the metal when they added that last little bit of silicon, something that made it just a little more brittle. To figure out why, we have to go microscopic. To solve this puzzle, you have to remember that a metal's properties all come down to its internal architecture, its microstructure.
So let's do it. Let's zoom in and see what's really going on at a level thousands of times smaller than one of your hairs.
And whoa, these microscope images tell the whole story. On the left, that's our super tough 0.68% silicon steel. See that? It's this complex interlocking web of fine needles. That is exactly what you want to see for toughness. Now look over at the image on the right. That's our stronger but more brittle 0.93% steel. You see those bigger, kind of smoother patches in there? That's something new. That wasn't there before.
That new stuff is called delta ferrite. It's basically a different arrangement of the iron atoms inside the steel. And look, a tiny bit of it is no big deal. But when you start getting larger patches of it, like we see in that stronger steel, it creates weak points. It's right at the border between this delta ferrite and the main structure where tiny cracks love to form, and that's what makes it less tough.
But wait, that delta ferrite is only one part of the story. To get the full picture, we have to look even closer at these tiny particles that are embedded inside the steel structure. Think of them like nuts in a fruitcake. They're called precipitates, and they are absolutely critical for strength.
So check this out. This image shows us the first type of nut in our fruitcake. The steel is made of all these little tiny crystals, or grains, all squished together. And these larger, bright white particles you see here, they're full of chromium, and they love to hang out right on the boundaries where those grains meet. They act kind of like mortar between bricks, locking those boundaries in place and reinforcing the entire thing.
Okay, now we zoom in even further, and we find a second, much smaller type of particle, and these guys are scattered everywhere inside the grains themselves. See them here? They look like tiny little speckles. Think of these as millions of microscopic speed bumps. They physically get in the way of any defects that are trying to move through the metal. It's that movement that lets a metal bend and break. So by blocking it, these tiny little pins make the steel incredibly strong. It's this amazing two-level reinforcement that makes the stuff so special.
All right, so we've looked at the strength, we've looked at the toughness, and we've peered deep inside at the microscopic structures that make it all happen. We've got all the pieces of the puzzle. Let's put them together and find our winner. What is the absolute best recipe for this super steel?
The answer, the perfect Goldilocks number, the one that's not too little, not too much, but just right, is 0.68% silicon.
This recipe just nailed it. It hit the absolute sweet spot. It gave us the highest possible toughness, which is so important for safety, while still having amazing strength. Its internal structure was fine and strong, and, this is the key, it managed to avoid creating those big, brittle patches of delta ferrite. This is what modern materials science is all about. Not just mixing stuff together, but precisely controlling the tiny structures inside to get the perfect balance of properties.
And that really brings us to the final big idea here. This isn't just about one kind of steel for one kind of reactor. This whole process is a perfect example of what we call materials by design, where we can literally tune a substance at the atomic level to overcome some incredible challenge. And it really makes you wonder, right? With this level of control, what other technologies that we once thought were totally impossible are now finally within our reach?